Okay, one more little piece on electric fields, and that is that sometimes we have more than one charge creating the field, right? So we might have a charge at this point. We're going to call this point A. We're going to say the charge is negative 12 microcoulombs. And then you might have a charge down here as well at point B, and we're going to say this charge is negative 15 microcoulombs. And then a charge over here at point C, and we're going to say that this charge is positive 8.1 microcoulombs. Okay, and so then and these are like on this side. And so the question might be, so what's the total electric field at point D up here? Notice there's no charge up here, because to find an electric field, you just need the charge that's creating the field. So there's going to be a field at D from A, but there's also going to be a field at D from B, and there's going to be a field at D from C. So if any one of them were alone, there would still be a field there. So in this question, it wants to know, like, what will be the total field as a result of all three of them. So we have some lengths. We know this one is 18 centimeters, and we know this is 24 centimeters. And this is actually question number 28 on page 655. I figured I could do it as an example because there were plenty on that page, and these are kind of long, so I figured you wouldn't mind if I took one. So if this is 24 centimeters, and this is 18 centimeters. And so the length between D and B, that's a 3 of 4, so this is going to be 30 centimeters, right? That's really just a 3, 4, 5 triangle. Okay, so the first step is kind of like when we were doing the total force on a point, and that is we need to find the field from A at D, and it's going to be equal to KQA over R squared. So 9 times 10 to the 9th Newton meter squared per coulomb squared. QA is negative 12 microcoulombs, so times 10 to the negative 6. And R from A to D is 24 centimeters, or 0.24 of a meter, which of course you're going to square. And when you do that, you get 1.875, I believe. 1.875 times 10 to the 6 newtons per coulomb. Okay, so that's what the field is at A from B. And whoops, I lost the negative. And it's a negative. What does the negative mean? Okay, so remember that we'll come back and talk about that, but remember these are fields, not forces, so it doesn't mean repelling. Okay, so we'll come back and talk about, after we finish finding all of them, what the negatives mean. So now we're going to find the field from B at D. So we're just pretending A and C aren't there now. And so we do KQB over R squared. So 9 times 10 to the 9th Newton meters squared per coulomb squared times negative 15 times 10 to the negative 6 coulombs. And the distance from B to C, or D, excuse me, is 0.3 meters squared. And so when you do this math, you get negative 1.5 times 10 to the 6th newtons per coulomb. And then our last one, what's the field at D from C? So ECD is equal to KQC over R squared. So 9 times 10 to the 9th Newton meters squared per coulomb squared. Our charge is 8.1 times 10 to the negative 6 coulombs. And then the distance from C to D is 18, or 0.18 meters squared. Do the math again, and you get 2.25 times 10 to the 6 newtons per coulomb. Okay, so we have all three of our, oh, there we go, sorry about that. It was like, why do I have this black ridge? We have all three of our fields. So then what does that mean? Well, now we need to go up to point D and figure out what's going on. So this negative is simply, there's the charge creating the field is negative. And what that means is the field lines from A are going out in all directions, right? Because that's what they do around a negative charge. So this field line that's going out along the line that D is on is going to keep going out, and it's going to be going this way. Okay, so this is the EAD. B is also a negative field, and so that means B is a negative charge, so that means the field lines again are going out in all directions around B. So if you follow the line that goes from B to D, the field up here will be going this way. This is EBD. And C's is positive, which means it's going down, because positive means all the field lines are going into C. So on the line that's connecting C and D, the field would be going down here. So if I redraw it down below to make it easier for us to see, here is my D. This is EB, and it was 1.5 times 10 to the 6th newtons per coulomb. Notice I've dropped the negative now. This one going out here is EA, and it was 1.875 times 10 to the 6th. Again, the negative is dropped because it was just telling us the direction. And C is going down like this. EC was 2.25, I think, times 10 to the negative 6 newtons per coulomb. So what do the positives and negatives mean? It tells you the direction of the field lines coming from the different charges that are creating the field. So now, oh wait, and we could also find an angle here, right? Oops, I don't know what I just did with my pen. Okay, this angle is going to be 36.87, if you found it, which means so is this angle. Why is that important? Because when we go to find the net field at D, we're going to need to find the components of the one at an angle so we can add them together. So EBY, this is 36.87. So EBY is going to be the sine, so it's going to be 1.5, this pen is dragging on me, 1.5, I don't know what I did with my other one that I just had, 1.5 times 10 to the 6 newtons per coulomb times the sine of 36.87. And this guy coming out here, EBX, is going to be 1.5 times 10 to the 6 newtons per coulomb cosine, because it's the adjacent side of 36.87, right? And so if we find these two, sine is 0.6, this is going to be 9 times 10 to the 5th newtons per coulomb, and that's 0.8, so 12. 1.2 times 10 to the 6th newtons per coulomb. So we now have everything going in x and y directions. So we can now add up, we can do sum of the fields, just like we would do sum of the forces. So sum of the fields in the x direction, they're both going the same way. So it'll be 1.2 times 10 to the 6th newtons per coulomb plus 1.875 times 10 to the 6th newtons per coulomb. And when you add those together, you should get 3.075 times 10 to the 6th. So that's our total in the x. Okay? Our total in the y, they're going in opposite directions, so you're going to have to subtract. So the total field going up is 9 times 10 to the 5th newtons per coulomb. Going down is 2.25 times 10 to the 6th newtons per coulomb. So the total in the y is going to be 1.35 times 10 to the 6th, and it's going to be a negative, and that negative just means it's going down. So now we redraw it. So we have to the right 3.0, is it 75? I think it's off the screen now for me. Times 10 to the 6th newtons per coulomb